So today we have our speaker Simon Du from University of Washington. Simon Du is currently assistant professor at the University of Washington. He did his PhD in CMU and his postdoc in IAS, Institute for Advanced Study. Simon is broadly interested in machine learning, especially in deep learning, representation learning, reinforcement learning, and also data selection. And today he is going to tell something about large language model reasoning with surprisingly only one example. Let's welcome Simon.
Thanks for the introduction. And I know today is a Europe's deadline. I hope my talk's not too technical to refresh your mind a bit. So today I'm going to talk about reinforcement learning for a large-scale model, and mainly talking about how the data functions in this paradigm. Okay, so I assume everyone here knows the basics about large language models. So here we are considering one step in training large language models called reinforcement learning with verifiable reward. It's in the post-training stage. In the post-training stage previously, or even nowadays, reinforcement learning with human feedback, RHF for short, is very widely used. You can get some human feedback for preference data, and then you tune your model to align with human preference. This approach often requires a trained reward model to provide this reward signal, and they can have several issues, like you need to hack the reward to a certain, to make the training stable. You need to have an accurate reward, but this reward needs to be estimated. Also, it involves high training costs as well. So here, what we are going to study is reinforcement learning with verifiable reward, and it's becoming more and more popular nowadays, especially for training the reasoning capability of language models. So reasoning including like math problems and say coding problems, where for those kind of problems you can have a rule-based reward, or basically another word, you can decide whether the outcome is correct or not. Okay, so here's a paradigm how we use what we call verified reward to train large language models, say mainly for reasoning tasks. So you have a training data. Let's say here is an SI. You can imagine it as a math problem. You use it as a prompt. Okay, put that into your language model. You can also view it as a policy in the language of reinforcement learning. And then the language model will output the answer, which is known as AI here. And then we have a verifiable reward. Basically, it just checks whether the answer is correct or not. If the answer is correct, you get some, say, positive non-zero reward, say gamma or something. And if it's wrong, then you get zero reward. Okay? In this way, you get some feedback so that you can further tune your language model. Okay, so at a high level, you can still use a kind of policy or gradient updates. You have some loss function that depends on the outcome of verified reward. Also, of course, your input data, and then you can use gradient update to update your language model policy. Okay, so that's the basic paradigm of reinforcement learning with verifiable reward. Okay, and why I said it's become more and more popular, because DeepSeek use the verified reward and achieve pretty high accuracy on some common benchmarks. And also in their papers, they claim they use a new algorithm called GRPO. This is the kind of the formula, which is even stronger than the previous algorithm like PPO. So here, let me dig a little bit into this formula, because later we'll do ablation studies on how different parts of this loss function actually affect the final performance of language model. So I'll just briefly talk about what are these terms. So basically, for this GRPO algorithm, let's say you have a set of math questions, and then you have a distribution over the math question, and every time you sample one question, so that's Q is like one question, let's say from the data set. Let's say you have a PBQ is like distribution of your data set. Okay, so here, one special thing about this GRPO is that for each question during your training, you not only output one answer, because for language model you can always have this random output because of temperature is a non-deterministic. So here it outputs say in total G different outputs. It can be different for a single math question. It may output different answers. Okay, which we denote as O1 to OG. Okay, and then these are your answers, and then for each answer, of course, you can get the reward based on the answer using this verifiable reward. Basically, if the answer is correct, you get reward 1, otherwise it's 0. And then this is the loss function, depends on whether your answers depend on different things, depends on your current policy, which we denote as pi old, theta old, and you want to optimize theta is your parameter, so it has a kind of policy ratio there, also some clipping to keep the training stable. There are another important term here, which is scale divergence. In large angle model, you don't want to deviate your new or fine-tuned model from the pre-trained model by much, so kind of control this distance from the pre-trained model, and thus we use this scale divergence to control this distance. And how you use different outputs. So this is something special about the GRPO. It's quite interesting where the use is called relative advantage function. So you have in total G outputs. You can have G rewards. So you compute the mean and standard deviation. So you can have a relative estimation of how good one particular output, say I, whether it is good or not. So you can compare Ri minus mean divided by standard deviation. That's like a relative advantage. So you use this as a the loss in the loss to update your parameter. Yeah.
So you've got 3 different thetas here, right? You've got pi theta old, and pi theta ref.
Yeah.
You want to say something about?
So ref is your pre-trained model, your base model without any training, like what you have. Theta old is your current iterations parameter, and theta is what you want to optimize over. So we want to basically update from theta old to theta n. Okay.
So I've got a batch. There's one over. This is an average over capital G.
So this is actually for a specific queue. You have one. For a specific queue, this means you have one question. Okay, and then G. In total, you have G answers.
Right.
Yeah, and then
I'm just wondering how the theta old is related to the batch G's.
Oh, so the answers you generate is based on your current iteration, which is theta old, current iteration parameter, right? So you have current iterations larger model, which has parameter theta old, and you use this language model, current iteration language model, to generate G answers. And based on G answers and the verifiable reward output feedback, you update from theta old to theta. Yeah, so that's just give you a sense of like what the different terms are, and then later I'll talk about what are the kind of important terms that actually makes a language model work. All right, and also by the way, people call this part. If you ignore this scale divergence, the first part, they call it policy gradient loss, because this is like the in reinforcement learning language is related to policy gradient, and depends on the feedback as well. All right, so after DeepSeek and just GRPO paper, there are a long line of follow-up work to try to improve the algorithm. You can see here, there's like Dr. GRPO, there are like reinforced plus, YMPP, and so on. That's not our focus today. Here we focus on how data affects the reinforcement learning with verifiable reward paradigm. Okay. So this is the question I want to answer. So to what extent can we reduce training data set? So in standard benchmarks, they use like 1,000 or even tens of thousands data to train or math questions to train the language model. And but here, let's say we want to reduce the data set and how much we can reduce. And surprisingly, we found that actually you only need one data point, one training example. You can already achieve comparable performance as if you are using the entire data set. Okay? Yeah. So I'll tell you about the more details about our funding. So here, let me first set up the stage. How do we evaluate the what we call reasoning capabilities of the language models? So nowadays, people often evaluate from different aspects of reasoning. One important domain is math. Okay, so there are several now become the standard benchmark for math reasoning tasks, Max 500, AME. AME and AMC, there are math competitions, and there's an Olympiad bench, things like that. So here, just let me give you one example from Math 500. For example, convert the point 03 in rectangular coordinates to polar coordinates, and then you need to enter your answer in a certain format. Okay, in that format, like R and theta. Okay, okay, so that's one standard example from these benchmarks. And in our work, we also tested the reasoning capability of other domain. There's an ARC, easy and challenge data set or benchmark. Its question is something like this. George wants to warm his hand quickly by rubbing them. Which skin survey produce the most heat? Like this for 4 answers. So because the dry prompts, you have higher friction coefficient, so actually you need dry prompt will give you produce the most heat. So that you need this kind of reasoning to get the correct answer. So this is another benchmark to evaluate the reasoning capabilities of language models. Okay, but here we mainly focus on math. But we will show you that even if you train on the math data set, you can also improve the reasoning capability for other domains as well. All right, so here let me show you the result first. Okay, so here we call this one-shot RLVR because we only use one training data. Okay, so our base model here in this example is like Q1 2.5 mass, 1.5B, and the data pool or training data pool is this 1.2K deep scale R subset. It has 1.2 thousand data points, and here we just select one data point from this 1.2K data set. Okay, so here are the results. So you can see here this dark blue line is between this blue line. Okay. Light blue one is using this entire 1.2K data set, and this corresponds to you can now see, but can achieve one of the line here. Okay, in the end, you can achieve like 70-ish accuracy. Okay, evaluated on this Math 500 data set, and similarly, you can have that kind of curve for the performance on average over those 6 math benchmarks. Okay. And then there's also another data set that's larger, 7.5K, achieves similar performance as well. So here is our finding. Okay, we just select one data point. We call it pi 1. I'll tell you what this 1 or 13 mean here later. But you can see here at the beginning, well, its performance not good, but after you train many steps, in the end, actually you can achieve comparable performance as if you are using the entire data set. Okay, and here's one example using pi 1, and there's another math problem, pi 13. You can achieve similar result as well, which is this darker green line. So this one is this lighter one. Okay, and here I also try 2 shots learning. Basically, we use these 2 examples as our training data. This corresponds to this line. You can see here it's very similar to the performance of using the entire data set. And it's not only for this one particular data set, even we evaluate on the 6 benchmarks on average, you can see here in the end, the performance is quite close to using the entire data set. Okay, so this is what we can observe. So here are some more detailed results for all these benchmarks, this 6 benchmark on average. For Math 500, you can see here all of them are pretty similar. There's a little bit gap for, oh, by the way, this yellow one is base model without any reinforcement training. Okay, and for AME, which is you can arguably say is harder because these are mass computation problems. There's, you can say, still some gap for these. There's 20%, you can get 70.5%, but sometimes you can get better. So it's, I would say on average, actually all of these methods or using different data to train actually get very similar performance. Okay, any questions? Yeah, so this is our key finding. Later, from now on, I'll just show you different ablation study, like how it affects, what term actually affects this one-shot RLVR, and how it can, and how we select these examples. Okay. Okay. Yeah. So here's another example on non-mass data set I talked about earlier. Okay, so the first line is a base model without reinforcement learning on these two data sets, ARC-E and ARC-C, like 48% and 30.2%. And then these two lines are you further using reinforcement learning to train with this two data set. Okay, then actually even if you only train on mass data set, you can still improve the reasoning capability on other kind of reasoning tasks as well. So again, these are the improvement. And here actually we can observe that similar behavior as mass data set. Here we only use one or two training example to reinforcement learning, train the model, and then actually you can even get higher accuracy compared to using the full data set. And this, remember, these are mass training data, and they can improve other reasoning capabilities as well. Yeah.
I'm not an RL person, but did you vary like the seeds and do multiple runs?
Yeah. We tried that.
I see. And so, what was the standard deviation or variance?
So
like?
the curve here, if you run multiple runs, I mean, the end is all of them will be run here. I mean, like this could be the standard, like the random standard deviation. So, but the curve, with different random C, the curve, the trend is still here. But you can see even within one seed, there's still randomness. But that could be the standard deviation, like around that large. I forgot the exact number,
yes.
but you get the sense, like it will be around here. Yeah.
Thank you.
Yeah. Any other questions? All right. Yeah, so here, let me first talk about how we actually select the data. Okay, so here, just a setup. We have this kind of loss function. We use the framework of VRL. It's a very user-friendly framework to deploy any kind of reinforcement learning algorithm. And basically, you just need to tune three kinds of terms. One is the policy gradient loss. One is called the scale divergence. There's also another term, it's called entropy loss, which is a standard entropy formula, which with like alpha smaller than 0, basically this term to encourage you to output something more random, closer to the uniform distribution. Okay, so how we do the data selection? All right, so we are not claiming we invent some groundbreaking data selection method. Basically, we just use some existing funding and we design a metric to select or sort data based on some scores. So previous work find that the variance of the reward signal is very important. Okay, generally speaking, the larger variance is better. There's no clean reason why or clean theory why this is the case, but this is an empirical finding. So that's one. Secondly, when you do data selection, problem is like a medium difficulty is better. So it's not something too hard, like those very hard math computation problem, but it's also not something too trivial, like very simple math questions. Okay, so basically we just based on these two intuition, we design called historical variance score to rank the data. So here, actually, we use all the data, and then we train them for epochs, okay? And for each data, we will have its training accuracy. That's basically is 0 or 1, okay? So it can be some 0 here, 1 here, but for each data, we can have different scores, okay? And then for each data I, we can compute the variance based on this scores. Okay, and then our remember we use this notation pi. It's just we just sort based on all the data points based on this variance. Okay, so it's pi 1 to pi n, and pi 1 has the largest variance, historical accuracy variance. Okay, so why this? In a sense, represent we chose a medium difficulty problem, because if the problem is too hard, it means you never get it correct, then your variance is low. And if your problem is too simple, then you always get it correctly, then you have low variance as well. So if you have a high variance, basically means you choose a kind of medium difficulty problem. That's the intuition. Okay? So we are, basically this is like some existing finding. People find this kind of data is more useful. And we just use this metric, and that's how we find the pi 1 in our the experiments I showed you earlier. Okay, and also we're not claiming this is like in any sense optimal. I think one very important future research direction is to design even better algorithm to select the data. Okay, so how do we actually implement it? So in neural network training, you have a batch. What we do, we just copy the single example many times to fill the entire training batch, like 128. And then each batch basically the same. It's a copy. Okay? And within the batch is also a copy of the same example as well. Okay. So this is for some technical reason, because this framework requires at least one example to allocate to each GPU. So what are the selected problems? So here's a pi 1, okay? So you can see here is like some pressure exerted on the wind of something, and then you want to find the velocity depends on the wind. Okay, so that's a question we found, and it also has, for this kind of question, you need to have a right format. Basically, in the end, you need to output in this format, and the benchmark will use regular expression to check whether you have this answer and whether this answer is correct. So that's how this benchmark is working. But this is the example we found. So you can see here it's not something too hard, because if you know the right formula, then you should get it correctly, and it's not too simple. Like you need to do some reasoning there. And similarly, this is pi 13. Again, it's not something too hard. It's not really a mass computation problem, but it's a not too simple as well. Okay. Yeah, just give you a sense of what kind of problem we select that actually have high variance. All right. So later we found that this is actually quite a universal phenomenon. So the specific example you use is not that important. Okay. So here's how we verify it. So we have the list of problems, pi 1 to pi say 1.2k, right? All of those problems sorted by the variance, and we just divide it into say 3 groups. So this is the top group, pi 1 to pi 17, and there's a middle group, pi 605, 606, and there's a bottom group which has the lowest variance. Okay, and these 2 lines, this 1207, 1208, actually in their data set the answer was wrong, but we still use that wrong answer to train the language model as well. So you can see here, compare with the base. So base only has 36% accuracy on mass 500, 6.7 on AME 24, but actually use any of the example to train, you can dramatically improve the accuracy. So again, this is only using one example, but actually using any of the group, you can have a big improvement. Yeah.
So to check the accuracy of an output, does that require the format being correct?
Yeah, only if your format is correct, you will get reward.
Could it be the case that you're just learning to put the proper format?
Yeah, that's a great question. Later, we also I don't have slides for this, but actually we have some follow-up experiments to try. It does get you more in the beginning of training. It does get you format to be cracked, but at that time it's now the scores are not as high as this. So later you can still further improve. Yeah, I don't have the slides for this, but later we'll update. After NeurIPS, we'll have a newer version for more results. But yeah, that's a very valid question. Yeah.
So you're sorting these a priori by the variance on the base model?
Yeah.
So I guess can you give me some sense of how that variance evolves during training? So what's the end variance of this?
Oh, end variance will be lower because you get more answered correctly. Yeah, we don't have. Yeah, that's a statistic I know. I don't have more with fine-grained statistics.
I guess another question is how much is the variance varying across this list?
Oh, it's quite high actually. Because those are, I would say, it's similar to the original intuition. Like if the problem is too difficult, then the variance is pretty low. Even in the end, you cannot get it correctly. But you can turn those medium difficulty problem from high variance to low variance to get it correctly. That's what we can observe. And for a very simple question, even from the beginning, you get it correctly. So the variance is low from the beginning.
But it still works.
Yeah, still works. It still can. I think one of these questions are a simple question, but still can get you better results. Yeah, so this is actually, so for this slide, I just want to show you this quite universal phenomenon. It's not something specific to that particular example. It's quite universal across different examples. Yeah.
Like why some samples only require like only 20 steps to conversion, or like some samples require 2,000 steps?
It's just different. So so there are also inherent randomness. I don't think we try each of the example many times. So there's some randomness there. Also, there are different difficulties. Yeah. For example, if for some very simple question in the beginning you got it correctly, and then you don't need many iterations to converge actually. Yeah. Okay, so that's the first phenomenon. Or the first message I want to show you, like quite universal across different examples. And secondly, it's also kind of universal to different algorithms. So basically, GRPO and PPO are arguably nowadays the two most popular algorithms. We also try PPO, it's another algorithm, and basically observe something similar on all of these benchmarks. You can compare. This is the baseline without reinforcement learning. This is using the full data set. This is using one training data. You can see here the phenomena is the same. You can dramatically improve the performance, getting similar comparable performance as you're using the full data set. So it's not something specific to GRPO. It's quite universal from the algorithm angle as well. Lastly, we want to verify that whether this is kind of universal across different models. So what I showed you before is some version of QN. Here also try some other like Llama 3.2b, 3.2, 3b model, also some DeepSeek R1, these two QN models. And basically the short answer observation is like you observe the same thing. Like using one example, you can achieve comparable performance as if you are using the full training data set. So it's also it's not like model specific, it's quite universal across different models as well. Okay. All right. So that's some slides I want to show you that it's quite universal phenomena. Another interesting phenomena I want to show you is what we named as a post-saturation generalization. So you can imagine you have one training example, so you can easily get that example converge or get very 100% accuracy very quickly. Okay. So you can see here these two plots. Basically, after several steps, you can get 100% accuracy. And later, because you have this entropy term in your loss, actually later that will give you more random output. That's why later actually sometimes the accuracy will drop. But basically to overfeed this data is very simple. Like a few steps, you can get 100% accuracy. And this is what you can observe using the full data set. Here, because you have 1.2K data, you do need more iterations to converge. Okay. However, if you look at the task performance on the evaluation, yeah.
How does accuracy on one sample go below? It's gonna be either 0 or 100. Like, how is there like less than 100?
Oh, because it's
0 accuracy.
no. So here for each iteration, you remember you can output G outputs.
Oh.
Yeah. So it's during training you can output more than one answer. So you can have a non-zero one. For evaluation, we do track the pass at 1. Yeah, metric. Yeah. So here, few iterations you can get 100% accuracy. However, for evaluation on the 6 benchmarks, you can see here, even after you overfit one particular data, the evaluation performance actually still increases. Okay, so this is similar to it's kind of an implicit regularization. I know many people doing research in that direction here. So here, after fitting the training data, 100% accuracy can still get improvement afterwards. Okay, and this is something we can empirically observe.
It's confusing to me, this observation, right? Because if
Uh,
you were pegged at 100%, if you were truly pegged at 100%, then there would be no difference.
Yeah, there's
between
a
that problem in training on something that just returned
yeah,
one.
that's a great question. So so here it's not because we output say G outcomes, it's not exactly 100%. So there's
So you're still exploiting that
yeah, there's
small
some
error.
randomness in
You're still
that
exploiting
output.
some small
Some
error
small perturbation that actually give you important signals to further improve the model. Yeah. All right, so that's what we call post saturation. Let's dig into one example. It's what we found is very interesting. So this is an example. Remember the example is like the physics, like remember the pressure, the wind velocity example. Here, this is without any training. This is what this language model will output. It lists some steps, and it does have the right format. But the answer is wrong. Right answer is 12.8, but this answer is 12.88. And this is one example from the evaluation data set. Here, in the beginning, it doesn't even output the correct format in the beginning. Okay, so this is what we can observe after 500 epochs. Okay, give you quite good reasoning, right? You can start by writing mathematical relation for the pressure, so you pick the right formula, and then right answer as well. So here you can see here is giving you better format and the reasoning format as well. And try to simplify this equation, blah blah blah. Although in the end, the answer is not correct. Okay, and later we do see that it's getting something I would say bizarre. So here in the 1300 steps, give you more refined answer and get both evaluation and the training example correct. And for evaluation, it's similar. Even if you train to say 1860 epochs. But if you look at what you can observe for the training example, it's really overfits or putting some random things. Although in the end, it is correct. But if you look at the reasoning, it's something purely random. Okay, so this is one surprising phenomenon we found. Perhaps it's due to the exploration or the entropy term in the laws. Somehow, even though you have this random output from the training data, for the evaluation output is still quite clean and reasonable. So we don't have a theory for this, but this is a very surprising phenomenon we can find. Yeah.
Did you evaluate like how does the length vary when you?
Yeah, I'll show you later. I'll show you later. It's in one of my slides. Okay, yeah, so in this 1860 epochs, it all certainly overfit the training example. The answer is correct, but the reasoning is completely random. So that's, again, it's related to implicit regularization, but I think is a very important or interesting research direction to study why this is the case. Yeah. Okay. Okay. Another interesting finding is that basically in math there are different categories like algebra, geometry, number theory, calculus. There are several categories in this data set, and actually it's not necessary to use. So first of all, using training example from one domain can improve the performance for all other domains. For example, Pi 1, it was an algebra question. Basically, use some formula, right? But it can improve all the domains also. Okay, and furthermore, you can see here. Let me see. Yeah. So here, let me highlight some numbers. So for example, Pi 11 is one number series question. Okay, using that to do reinforcement, you can get 66.1 accuracy on the number series questions. But actually, using some other domains, for example, Pi 13, which is a geometry question, you can get 83.9 accuracy. So it's not necessary to use the same domain question to improve the same domain's performance. Sometimes using other domain can also improve this domain's performance. Yeah.
Question: do you have an idea of the variance of the number, like the results for each category? Like how is the, like, for example, using geometry will increase the ability for number theory better than the number theory training example? Is that like consistent trend?
No, it's not. It's a quite example specific. It's not always. It's not like I use any geometry question is better than using number theory question to improve number theory. So it's just like we found. But it's not necessary that use number series for number series always better. Yeah. Yeah, so that's another finding. Again, we don't have answers for it, but it's quite general phenomenon here. All right, so back to the question on just the length of the output. Okay, yeah, we do observe longer and longer output. So here, especially using one training example. So here, or a few examples. So here, this is the response length. If you use a full data set, the output length is pretty flat, but actually if you use one training example, okay, then actually the response length is longer and longer. Okay, and also this also corresponds to the entropy loss, where it does become larger and larger. That's why in the end it will output some random things. Okay. Also, we look at this kind of what they call reflection words, like recheck, resync, those kind of words. And one observation is that these kind of words appear more frequently for the one-shot learning we use. You can see here, this kind of words appear more frequently, or number of these words, maybe not the frequency, but the total absolute number of this kind of words is more and more frequent. Whereas if you use the entire data set, it's not necessary to have this kind of words. So actually, we would say that one-shot learning and this 1.2K learning, they have qualitatively different behavior in the end. If you look at it through this, whether they have recheck this kind of words or the output length. So you can think about in the end, they have two different modes of language models. Okay, that's another finding. Yeah, so in the end, I would like to talk about different terms in the laws and how that affect the final outcome. Remember, basically we have three terms. Maybe let me remind you a bit. So we have these three terms. The policy gradient laws, which depend on the feedback. The KL divergence laws depend on the pre-trained model graph and the recurrent iteration theta. Also have this pure entropy term, which encourage you to output more random things. Okay. We also have you can also have a weight decay. So here we list the four kind of terms there. The policy laws the rate decay, the KL loss, and entropy loss. Okay. So first of all, without any of this, also basically, if you're testing the pre-trained model, you get the first line of result. You have 39.8 and 7.5 here. Okay, so first we observe that the policy loss is most important. Okay, so you have just using the policy loss alone, you can boost performance by a lot. Okay, from here to here. Okay, that's really the main driving force of the improvement, which is as expected because policy loss give you feedback. Okay, and then with rate decay, it doesn't improve by much. Okay, so rate decay is also not necessary there. And then if you look at, you add further more terms, for example, this term and this term. So KL loss also alone doesn't, or adding additional KL loss doesn't give you much improvement as well. But the entropy loss actually does give you more improvement. You can compare this line to this line. So that's also significant, on this scale, a significant improvement here. Okay, so that's we add one term one at a time. And then, so based on these, we would like to argue that this is something different from the Grokking phenomena, which is also related to implicit regularization, where after you overfeed the data, training data, you at some iteration you suddenly get very high accuracy. That's the Grokking phenomena. But here we will argue that it's something different because usually in Grokking, or most of the time, you do need a rate decay to have this improvement in Grokking. But here, without rate decay, you can have this post-saturation. So we will say that it's a different mechanism from the Grokking observed in earlier work. Okay. Yeah.
You are regularizing the KL to the reference.
Yeah. So that's
Is that analogous to a weight decay?
It's not the same because this KL is to regularize. I think intuitively, that is regularizing your model is not too far from the original model.
Well, the KL divergence is also asking that question.
Anyway, that's what KL divergence
Is doing.
Whereas the weight decay is to make your parameter smaller. So we think that's a different mechanism. Yeah. All right. And then we observe that this entropy loss is pretty important. You compare these three lines with all terms and including the entropy loss, give significant improvement compared to this line. And you can tune this a bit, also give you like smaller term. You can also give you improvement. Actually, if you remove KL loss, rate decay, only using policy loss and entropy loss, you can also get pretty good improvement compared to without using this entropy loss. So entropy loss actually is an important factor. Okay, and then we just further tried, without this policy loss, but we add entropy loss, which corresponds to this line. Okay, you can see here, just adding entropy loss itself, you can already achieve improvement on this mass 500. You can see here from 39.8 to 33.4. Okay, so that's kind of surprising because entropy loss actually doesn't require any label feedback, but you do. It just adding more randomness, you can get higher scores there.
Would that indicate that just increasing the temperature of your base model?
Yeah, that's something almost equivalent, I would say. Yeah, there may be some interesting problem on original base model. So after you add entropy loss, you can some randomness is more important. Yeah, so. Yeah, so this is our finding. So this is like you need to add the proper entropy loss to in core exploration, you can get better results. So just some ablation study with different temperature and entropy loss. You can observe that is entropy loss is pretty important. And this is result for adding entropy alone. I talked about earlier is already give you some improvement as well. And this is more ablation studies for different models, and again, adding entropy loss alone can give you improvement. So it's again quite surprising. Without any label, actually can get improvement. So that's another interesting, I think, theoretical problem to study as well. Yeah, so I hope this talk to give you a sense like there are actually more questions to answer than giving any specific serial answers. But all these empirical phenomena are quite surprising, and in the future we'd like to understand why. So in summary, one implication of our finding is that the base model already has strong reasoning capabilities because you only use one example to train it. You cannot believe that this one example can teach you everything about algebra number theory. So it means that in the original base model, it already has a strong reasoning capability in math. It just somehow this one example can make this language model output the correct or using the right tools to answer the question. Also, we find that how to select or curate proper data for reinforcement learning with verified rewards is very critical. Although using any example can give you a dramatic improvement, but if you select the right one, it still can give you further improvement. So, how to a general question: how to curate a good data set, and how do you actually use those data in a better way can be very critical. And theoretically, we want to understand why this can happen in the first place, and also how do we explain this for post-saturation generalization phenomena. It's basically like some kind of implicit generalization there. Also, we found entropy loss is very useful. It encourages better exploration, but itself is not super stable, so there could be better algorithm to stabilize the training procedure while maintaining the effect of entropy loss. And here we only tested on math and some reasoning tasks, but another big domain in reasoning is coding. We haven't done extensive experiments there, but it could be interesting to try how many data you actually need to improve the coding capability of the base models. Okay, and in the end, I want to thank for my collaborators. The first author is Yiping Wang, my student, and it's an extensive collaboration with Microsoft, and thanks to their GPU support. And I'm happy to take more questions.
Could you speak a little more about how you know that you're not just teaching the model to put the answer in the format that you like, and you're actually...
So later we did some experiments. Basically, how do I say? We can observe that after several epochs, all the questions have the right format. The answer in the language model can output in the right format. We can check that just by checking the regular expression. However, their answers are still wrong in the first several epochs. So from that epoch, later it's not only about formatting. It will be something on the inherent capability, I guess. So basically, after several epochs, we check the output of those benchmark data set. Actually, you do get the format correctly, but their answers are wrong. So the later epoch actually improve the rule reasoning capability. Yeah.
But do you have a separate format loss?
No, just entropy. Just a policy gradient loss.
I see. But you give instructions.
But every iteration you can check the format is correct or not.
But you give instructions about format in the prompt.
Yeah. The question is like you do have. Sorry, let me pull out the question. Yeah, the question. Yeah, output the final answer within this format.
And you even get this format correct, just training it with entropy loss without any supervision. So it's like model is not learning the format by the supervision.
Yeah. That's also surprising. We don't understand why.
So prompt and the entropy loss teaches the model to learn the format.
Yeah. You can realize that. That's possible. So.
Just to think about that, if you ran the thing at temperature 0, then if it gets it, so that makes it deterministic.
Right.
And if it gets it wrong, it's never going to.
Right.
The reward's going to be 0.
Yeah.
If you increase the temperature, then you're gonna get some probability that it's correct.
Yeah.
And so I can sort of, is that a reasonable way to think about why simply increasing the temperature would improve your scores?
Yeah, I mean, you do need this randomness to improve to get the.
But you showed that randomness alone
Yeah.
can improve the score, right?
Right,
Which
right, right.
suggests that simply increasing the temperature.
Yeah, I think here we look at pass at 1, so.
Yeah, but, right, so passive one could be 0 if it's deterministically wrong. But if you raise the temperature, you get better.
I think we tried that. Let me see. I think I showed you one plot here. I think this is with different temperature, if I remember correctly. Yeah, so you do observe with different temperature in the beginning. The performance does have a different. Actually, not really. I think from here it's similar. It's we didn't tune it by much. It's like 0.6 or 0.1.
But is this only temperature, or you're also training?
I mean, if you look at the first iteration, then that would be the only temperature, I say. So, yeah, but that's a valid question. I don't think they're exactly equivalent, but they may have similar effect. Yeah, that's maybe we should do some study on that.
So did you to make this like an extreme situation, if you just take a random prompt and train it with entropy loss, do you think it will still help? Like not even.
I mean, if your temperature is too large, then it will not work, I think.
No, I mean just reproduce the current setting with entropy loss only, but you don't make the prompt be something meaningful about the.
Oh, I see. That's a good question. I mean, the prompt itself does not have the.
Yeah, it's kind of completely irrelevant to the task. Do you think that still works? Do you think like something?
Maybe not. I mean, we haven't tried, but maybe not.
Yeah. No questions?
Any more questions?
Okay. If no questions, let's thanks our speaker again.